Yeah, okay. So I'm Jordan, and I'm talking about ocean wave propagation in the marginal ice zone on the transition from consolidated to broken ice covers, which for those who were there yesterday will be very familiar, kind of like the last picture that I talked about. It's new work that we're doing, that I've been doing with Luke. We're both at the University of Adelaide. Also want to thank the Australian Research Council for funding this work. And finally, of course, the Isaac Newton Institute for having me here. It's been lovely, and especially nice now that summer's finally come. So excited about that, and sorry to be holding you in, I guess. Okay, so Adelaide, South Australia. Just, I guess, hitting Luke's note about personal history of myself. I was born in Brisbane, which is part of Queensland, which is this state here. Brisbane's down here. I am Indigenous Australian, so from the breakup people, which from like up here. And my last name, Pitt, comes from Torres Strait Islands. It's a very English name, but actually, you know, everything that happened, colonization, comes from the Torres Strait. It's a very famous pits, and if I meet anyone from there, they recognize me immediately. It's my last name. Okay, I'm now in Adelaide, which is this white circle here in South Australia, which is a red state. And it's not it's a red state actually. Although all of it's red now. That's a bit of an in-joke about political parties. Okay, so of course it has lots of natural wildlife that you'd all be kind of interested in. And obviously I'm the expert being, you know, born and bred Australian. There has beaches, lovely beaches, although unfortunately not many waves at the beach, but it's still quite nice to swim around. My partner enjoys that more. My fiance enjoys that more actually. And wineries as well, world-class wineries indeed. And indeed, from some of them, you can actually see the beach and go down and swim. So you can, you know, start a day up in the winery and go finish for a swim. So that's pretty good. And the university in the city is quite lively as well. So especially at the start of the year, all the new students are coming and we have fringe on. So it's quite a lively experience, which is really nice. Okay, now for the university. Very prestigious, an old university for Australia from 1874, has more than 20,000 students, 3,000 staff. Ranks very highly, punches well above its weight in the top 100 in the world rankings, and very prestigious for an Australian university. And it's hosted some amazing mathematicians, applied mathematicians, like Ernie Tuck and Ren Potts, and the Bragg brothers and Horace Lamb both spent time in Adelaide. So yeah, we've got a lot of history here, which is great. Yes. Yeah. Yeah. I guess there's a good tradition here of English people coming to Adelaide and getting Nobel Prizes. So maybe Luke can say something about what his plans are.
Well, they moved back to England.
Yeah.
Nobel Prizes back in Manchester, and he moved out to Adelaide 2 years. Cambridge, then Adelaide and Manchester, right? But they bought it. So the story is that they wouldn't then get married in Cambridge, right? So academic. So he got 6 months to Adelaide.
The state of free love, Adelaide. Okay, so I'll take you a bit further south now, to the marginal ice zone. So in particular, we have the ocean surface freezing because of how cold it is. And when it does, we have a particular section of this ice-covered ocean called the marginal ice zone, where ice comes in these forms here. We see these chunks of sea ice separated by open water or a slurry of ice crystals, which is more what we see here. And the reason we get this marginal ice zone, one of the reasons that leads to the development of this kind of particular form of the sea ice cover, is that the sea ice cover is impacted by waves, which are generated out in the open ocean and then pass through and into this ice cover. You can see this nice video here, although it's a bit framey due to the Zoom link, unfortunately. But we can see these waves here, kind of going this way. And in terms of ocean waves, they look a bit different, and it's basically because they're longer. Essentially, all those high frequencies have died out, which we'll kind of get to as we see. And yeah. So this marginal ice zone is a result of the interaction of sea ice and ocean waves. And here's a kind of diagram trying to kind of summarize and give you a sense of how complex the interactions are between everything that's happening down in the Southern Ocean. So we have the sun, which provides heat. We have wind blowing across the ocean, which generates the waves indeed, those ones that we saw anyway. And we have snowfall as well. And then we have our ocean, which is also another kind of complex dynamic system. And to the south, which is to the left on this picture, we have Antarctica, and then to the north, we have our open ocean. And there's a bit of scale here as well. The ice is kind of on the order of meters. So waves come in from our open ocean, generated by wind blowing across the ocean surface. And they come into this ice field and cause lots of complex interactions that we'd be interested in modeling that are going to, in turn, influence the climate, as we'll see. So we have breakup. As the waves propagate, they flex and strain your ice cover, and this can, if the waves are sufficiently strong and energetic, break them. We also have drift of the ice. So due to the combination of the waves, but also the wind as well, the ice can move a very significant distance over a very short time, especially in very strong storms. And this kind of points to, we have things, the ice cover breaking and being opened up by this drift. This allows more sunlight into our ocean, heating it up, which can enhance the melt.
Well, the drift is due mainly to wind? Is it known?
I mean, it's all very coupled, especially in a very strong storm event.
Depends on the time scale.
Yeah. No.
Wind is the common driver of shorter time scales. And currents within.
Yeah.
Near inertial time scales.
Another kind of melt event, or a kind of thing that can add to melt, but also I want to point out, it's not just melt that's going on, it's also growth, is overwashing. And I kind of showed a video of that yesterday. And this is the process by which waves push water onto and across the surface of the sea ice. In this process, of course, if we have a small amount of water on our ice, then we can let more sun's light in, which can enhance melt, but we can also, in winter, deposit ice crystals onto the surface of our flow. So it's important for both growth and melting. We also have herding and rafting, which is due to the wave action as well, and some of the wind. And when the herding is close enough, we can actually have the ice building, crashing and rafting on top of one another, which is a dominant source of growth of very thick ice.
I think, what does herding mean? I don't know that word. Does it mean that they tend to want to stick together? Chunks of ice?
Yeah, so, oh, well, I mean, it happens in different locations, but in certain locations, you can get kind of the ice being pushed together, essentially, and herded in. You can see in some very nice pictures, very distinct bands of sea ice forming due to kind of the combination of everything going on. And also collisions. And this is thought to be one of the reasons why we had those flow kind of shapes. They were very circular in that first video, and that's because of the constant collisions between the different flows, kind of giving you a nice circular shape. And
the raised edges.
Yeah, and it has raised edges as well, which is also from collisions. The other thing that's shown here, that might be a bit less obvious, but maybe we should all pay attention to being wave people, is that our waves are decreasing over distance as they propagate. They're attenuating, which is a key thing. So eventually these waves die out, and then we can have kind of a different, or we can change the evolution of our sea ice. So it's very important to try and understand this coupling between the waves and the sea ice in this region to try and model it, which we can see kind of here. So this is a plot for the Antarctic, split between the two kind of seasons, summer and winter. And we're kind of looking around the Earth. The longitude is the x-axis. And we have our y-axis on the right, which gives us our blue curve as the sea ice edge latitude, i.e. the extent north and south that the sea ice is over decades. So we're looking at a kind of climatic scale, or a decadal scale, I guess. And the important thing to note here is that our y-axis is inverted. So up top is negative ice edge latitude, retreat, and down the bottom is ice edge advance. So we're also plotting the wave height given by the left-hand side in red. And there we have kind of the more standard axis orientation, where when we go up the plot, we have higher waves, and when we go down, we have lower. And what this is showing is that we have kind of very strong correlation between, negative correlation between the wave height and the ice edge latitude. So something interesting is going on that we should investigate.
I don't understand that. So what's wave height? Meter per decade. So what does that mean we do?
Yes. Yeah. So as the wave heights are increasing over the decades, we're getting this retreat in the ice edge latitude as well. Now there's kind of two processes, right? The waves are affecting the ice edge. Yeah. This would be like 79 to 2000 or 2020 or something, 10. Oh,
It was published in 2015.
and these would be satellite derived, right? And just looking at the extent, so not actually looking at the volume.
So, sorry.
Yeah, no.
This is on my slides. The ice edge latitude comes from satellites. The wave heights, which is proxy for energy, comes from a model line past. So the waves are taken as close to the ice edge as they can get.
Looking at the trend over the decade, so like kind of fitting a linear trend essentially.
So decade is time decade.
Yeah, yeah,
So it's a moving average of wavelength.
yeah, yeah.
It's a over decade with.
It's a trend, is it? The time series for the trend through it.
I guess I should have some delta maybe.
But this is the most recent decade.
Well, I guess it's averaged over because you're doing a linear trend over many decades from 79 till.
Statistically, it does not change over the decades. Well, no, I mean, we were having on Monday, Tuesday, whenever it was this week, right? And this is the standard in the start of these data sets. One of the lowest order statistics, you put a linear curve.
It means it's decreased, the wave heights have decreased.
Zero is the total average
Yeah,
for whatever number of years it takes.
yeah, I guess,
And then plus or minus about the whole.
yeah, I guess it's actually probably not the average, but what the starting value in 79 or what those heights were, as close to the ice edges that you get. And we're just measuring the wave heights, again by a hindcast.
Yeah, +3, I mean, that particular one should be to expect the average significant wave heights to increase range of 10 years on the future.
Yeah, I was more curious about minus.
3 meters.
Yeah. Relatively.
I guess it's also a complicated thing where we've kind of split all the degrees in longitude as well, like something else could be going on, like just kind of rotating around or something.
It doesn't tell you about the absolute value.
No,
Yeah,
For example, standard deviation.
No idea, I didn't do this. Probably.
I hope Alison's asleep, maybe. But the point of this is
Take it with a pinch.
exactly, and this is kind of related as well, is that, you know, we're looking at correlation, not causation. So, you know, be a bit wary, but something interesting is going on. There's also a lot of other studies looking at concluding that the wave heights have something to do with the extent of ice edge, not just this plot, but some other results as well. We'll have to have a look at that. Okay, but this is a mechanism you could think about as kind of how this might be causal and not correlations strictly. So larger waves push your ice edge back. This allows more heat uptake in the ocean by the sun's rays. And this increases melt and sea ice loss, which allows for more waves to get in. So that kind of one explanation for why the ice edge retreat might be associated with higher waves. You can also, there's also the advance as well, kind of associated, which is also interesting. Okay. Yes, positive feedback loop, of course, where you just have larger waves pushing everything back, and what I described earlier. Okay, so here's a nice video of sea ice breaking up due to a passing ship. Our ship goes down the picture, and it generates a wave which travels through this ice, which was initially solid. Or at least there's nothing obvious broken here. And this is done by Elie Dumas and Danny Dumont in Canada. The Canadian coastal ship, actually. You have these nice waves breaking up our sea ice. Again, it's kind of exposing some of the water to sunlight. So to kind of summarize what's going on while we're interested in this, the waves have many effects on the sea ice cover, for instance, breakup. And as I mentioned as well in the diagram we showed, the ice cover also has an influence on the waves due to both scattering between the ice flows, you can think about it like that, and also dissipation, which is a bit harder to give one process for, since there's many sources of dissipation. Like if you break the ice, you're losing wave energy. If you overwash the ice, you're losing a bit of wave energy, and these all add up and produce this attenuation that we observe very clearly over distance for the wave energy. So these are the current interpretation of observations, and also kind of the large scale wave models kind of are based on these types of thoughts. So this is a paper with a lot of big names in the field, looking at the Arctic marginal ice zone, which also has things. It's not just the Southern Ocean. And indeed, as the climate changes, we're getting more kind of an Arctic marginal ice zone, unfortunately. So yeah, big names: Collins, Rogers, Marchenko, and Baden. And they describe a three-phase interpretation of their observations. So in the first phase, we have very strong solid ice, we get wave blocking. So none of the waves get in. In phase two, we have breakup and the very dynamic evolution of the sea ice associated with very strong attenuation of waves. So there's a lot of processes going on that are losing wave energy, but changing the ice significantly. And then phase three, where we have like kind of a very broken, weak ice cover and very weak attenuation, which they further summarize as this binary zero transmission in unbroken ice and then total transmission in fractured ice. And then also in the Antarctic, I should say, they kind of have a similar view of observations looking at the marginal ice zone, where they have this on-off behavior, again, associated with very strong damping for unbroken ice, which is a bit different to wave blocking, I guess, and very weak attenuation for very broken ice covers. And this is the view that's taken in large-scale wave models as well, looking at just kind of binary or just thinking about changing the attenuation rate, comparing like a very strong solid block of ice to a series of flows. Okay, but this is actually quite a complicated process to observe. And so we'd like to do something a bit more controlled. And so fortunately, we have some experiments here. So this is a wave tank in Alto. They can freeze the surface of their wave tank, which is quite nice, and produce this ice cover. Waves are generated away from us and they're coming towards us. And a series of experiments were conducted. And this is the one where the ice cover broke. So it's the most interesting to watch, published by Giulio Pazzarotti et al. Luke was on that paper as well. So we can see those waves as they propagate through the ice cover. Under some kind of repeated stressing and straining, we get fracturing. And fortunately for us, it's a very one-dimensional kind of behavior. We get these bands of broken sea ice. Maybe we'll just watch that again. It's quite quick.
Say where the ice is. I'm not sure what I'm looking at.
Yeah, so there's kind of like, there's already some broken ice at the front when we start. And then there's open water up the top. And if you kind of focus maybe on these kind of like two, we can see that I think we start with very solid ice. Oh, yeah. Oh, maybe that's actually a perfect place to start. If we focus on these two, we start with solid. We don't see any breaks. And then if you watch it, eventually, yeah, we get some breaking.
This one points out that it's not entirely one direction.
Yeah,
It still breaks along the wave crest, but then afterwards it breaks in both equal direction, such that the minor axis is in the wave direction.
Yeah. Yeah, right. Or maybe they open the doors. Okay. Yeah.
Next time.
Was this doped as well? Like,
Yes, so
yeah,
that's
exactly.
right. It's done so that it's closer to sea ice in the fields.
Yeah.
It's very difficult to get stains right for that. It's a bit more.
Yeah.
Yeah, exactly.
Okay, so I'm going to try and summarize. I guess the 1D was more a comment on our summary of the results rather than what actually happened in the experiment. So I mentioned that we did that there was a series of tests were conducted. Sorry for the colors, but we have this consolidated ice floating on the surface. And for a particular experiment, test, I should say, the waves were small enough and they didn't break the ice cover. So we just have them propagating through this consolidated floating ice cover. And then for another one, that video I showed, we get waves through a broken ice cover. Now, this broken ice cover was indeed generated by the waves, and there's kind of some complication of the full coupling. But we're just going to consider and kind of think about what happens for waves just through a broken ice cover. That's going to be way easier to model, of course. So we have these results for the normalized wave amplitude versus distance. So we're seeing the attenuation of the waves as they propagate. So one being the wave amplitude incoming to the ice cover, so in the open water. And so we can see that over the first couple of meters, we get a very significant drop as it transfers from free surface to the ice cover. And then we have kind of a gradual attenuation over distance. Whoa, went too far. You can see that. For our broken ice cover, we get this kind of total transmission, i.e., we get very good propagation into that first couple of meters of the ice cover. And then we get curiously stronger attenuation over distance. Okay, so, I mean, it's a bit interesting. There's obviously a couple of explanations, right? Because the waves were breaking the ice and the waves are moving the ice around. But we're just going to see and look at this kind of transition from the consolidated ice cover to a broken ice cover and just see what our models say, essentially. So it kind of leads us to how do we describe waves in the ice cover? Well, we have to consider the attenuation rate, and that's usually what large models consider. They just try and look at having variable attenuation rates in different regions. But not only do you have to consider that, but you also need to consider this amplitude drop as you go from a free surface to this ice cover region. And as I kind of mentioned, the results motivate the model, but they will not be used for validation, mainly because of this complication of lots of dynamic things happening in this experiment that are hard to pull apart. Yeah, so we're getting, when waves come in, there's a bit of reflection, you lose a bit of that due to scattering, but you also get some generation of waves, evanescent waves, essentially, as you kind of see, and they both produce a drop in the attenuation rate. You can kind of think about it like, we get, as we go from our free surface media to our ice covered media, we have some new amplitude that's generated, the transmitted amplitude. That leads to the amplitude drop. And then once the wave's in the ice cover, it'll attenuate over distance due to like dissipation effects.
But it's not just propagation.
No, I know.
You show that.
Yeah, it's the evanescent. Yeah. We'll see that in the results. I mean, the model, I guess. Yeah. Yeah, exactly. So this is the interesting stuff that we'll get to. Okay. Yeah, I mean, no one's really interrupting me. We'll just go off anyway. We run out of time. So, yeah, we should report the beers. Okay, so we have this kind of simplified model for that kind of first experiment. We have some water with some depth H, some seabed sitting far below our ice cover, and then the ice cover has some draft D given by the Archimedean draft and some thickness capital D. we're going to model our water as potential flow, the rotational and viscid, all that fun stuff. It allows us to do kind of simple wave models, but still kind of complicated enough to have water waves. We have an impermeable solid at our seafloor. And an interesting thing here is the model for the ice cover. So we have a viscoelastic plate, a Kirchhoff-Love plate with some Robinson-Palmer damping, and what this allows for is the elasticity, we get bending, but we also have the viscosity, that attenuation, that dissipation over distance, as we saw in the experiment. And we're going to do kind of standard stuff. We'll look at our 2D model. We're going to have linear waves and assume the time harmonic motion. So kind of what all that's going on here, as we'll see, is that we have waves in our free surface, waves in our ice cover, and then we have to do some suitable solving of the scattering between those two problems by solving the problem, essentially. Okay, so this is our differential equation for the velocity potential given by linear potential flow theory. The Laplacian is 0 in our water. We have the standard vertical velocity is 0 at the impermeable boundary in the bed. We get this kind of funky thing from our linear viscoelastic plate, which matches the velocity potential in the water to the velocity in the at the boundary with the ice cover, essentially. And so what these terms mean is we have F, which is our flexural rigidity, which tells us how much our ice cover resists bending. We have our mass term, which gives us the added mass of the ice cover. And we have our gamma term, which gives us our damping rate over distance. And then we get a pretty standard free surface condition. I should mention that sigma here is our normalized wave frequency for the ice cover. Oh, sorry, for the whole problem, since everything's time harmonic with the same frequency. So these waves are moving at one frequency in time, and these waves are moving at the same frequency in time. Okay. So what we have here in the water is we have our incident wave, which has its wavelength given by the dispersion relationship, which is our linear potential flow theory plus our free surface condition. So it gives us our lambda W being our wavelength in water. And it's going to the right. It has normalized amplitude, so 1. And then we get some reflected wave back from this ice edge, which travels to the left with the same wavelength. And they're just linearly superposed because we have linear waves. There is some depth dependence, this zeta W for the water, which will be, you can kind of think about them as just waves. And then what the depth variations give us is the reflection and transmission coefficients, essentially, between the waves in the different media. So we can kind of ignore them in terms of thinking about just waves and scattering. And we get some evanescent terms as well, which we also have to do to properly match the velocity potential in the water and in the ice covered water. So that's just due to reflection in the initial incident wave. In the ice cover, we get this transmitted amplitude, A. We get a new wavelength in the ice cover, lambda, which depends on the linear potential flow theory coupled to that viscoelastic plate model. And we get an attenuation rate alpha because we had this imaginary damping rate gamma. We get a new variation in the depth, zeta, which is different, but again, just kind of helps us, or it doesn't help us. It determines what the transmission and the reflection coefficients will be when we match appropriately the velocity potential in the left hand in the free surface and in the ice covered water, plus these evanescent terms. Okay, so the model solves for this problem numerically. We choose some number of evanescent terms to approximate up to, truncate it, and then we can solve this numerically.
So this is happening in the water below the ice.
Yeah.
The effect of the ice being removed by your kind of one-dimensional model.
Yeah, pretty much. Like the ice cover kind of just gives us a new boundary condition at the interface, and you can kind of think about it as just two media with different boundary conditions.
Might be worth pointing out that this mask is not to scale because
Yes, ice is really thin compared to the
that's why I want to
yeah.
check
Yeah. Yes. Yeah. You get heave. So we in this picture, we have kind of neglected an important but more complicated form of motion, which is these. We have an additional 2 wave numbers associated with the rigid motions of our sea ice cover. Now the heave and the pitch in particular. So I will mention this at the end, but in terms of like our understanding, we'll just think about them as these types of waves and not just kind of neglect these complex wave numbers associated with the rigid motions. But the model does this, but I'm kind of ignoring that for the explanation of this. Okay, so we throw our numerical code at it and it can solve this problem pretty easily. This is done back in the 90s, yes. So we have our geometry here. Our ice cover is about 1 meter thick, we're not quite. And we have this plot of the displacement at a particular time of the 0 line, essentially. So this blue line is the free surface at a particular time, and then this cyan line is kind of the 0 line. So it's kind of like inside the flow. It's not exactly the bottom, but everything's linear. We kind of just match these two. Okay, so what we can see is our incident wave having an amplitude of about 1. So we don't get much reflection back in this particular example, although there is a bit. And then we have this wavelength oscillations over distance, which is in the ice cover with some fixed wavelength lambda, which is what we'd expect given the dispersion relationship. And then we have an attenuation rate as well. So we have the initial transmitted amplitude times this attenuation rate over distance exponential. And you'll notice that it lines up better with the second peak and not at the ice edge. And this is because of those evanescent terms, essentially. It decay very quickly, but it lines up very nicely afterwards. Okay, now what happens when we break our ice cover? So we're just going to take the example of 2 flows. Yeah. Yeah, sure. I should probably show that. Yeah, so we pick a finite number of the evanescent terms, essentially. And then we match variational forms based on those fixed approximations of the continuity of the velocity potential and its first derivative at the interface. And that gives us, yeah, but it's kind of like you're doing the variational form, you're not just matching one mode to the, you're not just matching the first to the first, the second to the second. There's relationships between all of them. Yeah. Cool. Okay, so now we have 2 flows, and we have the open water as well. So, but we kind of understand that, I guess. We get some reflection back, some incident wave, and then we have our waves. We have to consider now is that waves can come in, but they can also come back from that first flow. So we have to consider the rightward propagating waves with amplitude A1, which is this one. Again, we get the same wavelength and attenuation rate. And we have to consider the leftward propagating waves with amplitude B1. Again, there's some variation with depth. And as I kind of answered before, there's also going to be some rigid motions as well. But we can still just kind of look at this problem as reflection and transmission. And in our second flow, we get the same thing, right? And what the method does is it solves the complete multiple scattering problem. So the code just does this. You have an incident wave, you get a bit of reflection back, get waves going through the first flow, get reflected back, and then all the flows are interacting in this multiple scattering problem. And we can
Call it a multiple scattering problem.
What?
You might call it a multiple
Yeah,
scattering
exactly.
problem.
Maybe I should be at a workshop for it.
So that on the events and right, you have also you have the exponential growing one, and because it is around the magnet, right?
Yeah.
Okay, so when you said evanescence, it is just not only evanescence, but also the exponential growing.
Oh, no, sorry, yes.
Okay.
It's just the decaying ones. And
Just
when,
the decaying ones.
yeah, this is based solely on the dispersion relationship. When you solve it, the one that you only get decaying ones, you don't get any
But as soon as we're having the boundary, we can have both, right?
The decaying from one end is growing from the other,
Exactly.
vice versa, like, so. They're evanescent accounting consolidations.
Yeah.
There are all evanescent in some sense.
Yeah,
But one's more than the other. Yeah.
yeah, but only at the edges, right? So like you do get, well, I mean, we see a bit of that, right? Kind of here.
Yeah.
So we do get decay, but it only happens that we only get this evanescent mode. You can only feel the effects at the edges of your interface.
Because
Yeah.
Yeah, but maybe we have both, or we have also the exponential growth when you know.
It's normalization. So you normalize the growing ones to the next edge on, and it becomes by the day. So, it's,
Okay, so in some sense, you
it's
suppose,
just a way of thinking.
but you suppose that the distance is big enough so that there will only be exponential one. No.
No, yeah. But we'll see that. That don't seem to matter. Okay. So the code does this. And when we do that, we get kind of the same kind of plot we saw before. We have the geometry, we have one flow with about 500 meters long here and a second flow here. Inside each of those flows, we get the waves that we'd expect. So it has some wavelength, indeed the wavelength we saw before, and some attenuation rate, so it's a bit hard to see over this shorter distance. But when we go from our first flow to our second flow, we get a jump due to a combination, like the scattering, reflection, and transmission, and also, I guess, the transmission, that amplitude drop as well, which for this problem results in a bit more reflection as well in that initial water cavity. But the point being is that now, unlike before, we don't have this global attenuation rate. You can't just draw one exponential that goes over the whole domain. Although if you zoom out enough, maybe you can, but as we'll see. Yeah, in an average sense, you can talk about like the average trend of your amplitudes over distance. But, and this is kind of like that example I showed at the end of the last talk, if you break up your ice cover enough, and we take our flow lengths to be 10 meters, which is much smaller than the wavelength in water, which is 63 meters, which some might notice as 20 times pi, which is what it actually is. Then we actually get a different situation now. So we don't see any effect of the scattering. You can't see the edge of the flows in this. We just see a very consistent wave field with like one wavelength and one attenuation rate.
It's a periodic medium.
This one is a periodic medium. All the flows are the same length. Yeah, so something interesting is happening there. So how do we go? Yeah, mentioned we have kind of just a single attenuation rate now. We're in a homogenized regime with periodic cell, which we'll pick up later. Okay, so how do we transition from these kind of situations? And this is described in this plot here. So now my flow lengths are actually random, but they're random with some mean flow length. So on the right here is very, very long flows, i.e. consolidated ice. And on the left here, we have very broken ice, but it's still random. And then we've averaged, so to get 1 point. So this is kind of a mean trend for the distribution of flow lengths that I think.
You mean you ensemble?
Ensemble average, yes, yeah. We have a plot of the wavelength, our attenuation rate alpha, and the transmitted amplitude. So on the right, we get back to consolidated one. It's not too surprising. Consolidated wavelength, consolidated attenuation rate. And we get some drop in the amplitude as you go from water to my ice cover. So we're in this kind of consolidated regime where it's pretty consistent. And then at some point, scattering becomes important and we head into this kind of transition regime. Now here, this is definitely the part where that no global attenuation rate is going to be a factor, but if you average and it kind of looks nice, but there is complicated wave fields going on in there. And then after we break it up enough, like in that last example, we reach some homogenized regime where my wavelength is headed closer to water, but it's now just kind of leveling off. So if you break your ice further, you don't get any change in your wavelength. Likewise, in your attenuation rate, which is now larger than it was for the solid ice, which is curious, but matches the experiments. And we get this kind of full transmission into my ice cover. So, kind of mentioned it's periodic media, right? Homogenized regime. Well, what happens if I look at the periodic cells and what they're doing? Okay, and this is what we've done here. So we're going to assume that my flow length is really small. And then I assume that I have the identical flow lengths in periodic media. And then look at my unit cell from 0 to L and apply my quasi-periodic Watt conditions to the edges of my boundary. So we have, of course, the periodic parts being this connection between phi 0 and phi L, and quasi being my new exponential term, which has a complex Q in this example here. And the goal is to solve for Q, essentially. So, considering the scattering of waves across my unit cell, I have this wave, this blue wave coming into my cell. It's reflected with some reflection amplitude R and some transmission amplitude T. And I'm just kind of considering the propagating mode. I'm kind of forgetting about the evanescent waves, although you can consider them. Maybe it's a bit easier to think about just that propagating mode for now. So I have a 2x2 matrix. And what we have can use the scattering matrix generated by R and T to produce a transfer matrix, which gives you the waves on the right-hand side of my flow based on the waves on the left-hand side of the flow, which is P. If you've done any scattering, this is a very simple transformation of the original scattering matrix. So it's a bit complicated, but anyway, it just gives us the left-hand side, gives us the right-hand side, given the left-hand side is just P times that left-hand side. So what this means is that if I have a block number, some kind of wave field, and the quasi-periodic conditions hold, then it must be that my exponential term is equal to my eigenvalues of my transfer matrix, if it's true. But that's just the way we calculate it. You just assume that it is, and then solve for Q essentially. And that gives me these plots. So this is again, just a plot of the attenuation rate and the wavelength, since that's all the information in Q. My red is the method of just solving for P, determining P based on the scattering matrix, reflection transmission across the unit cell, and solving for Q, and just looking at the real part to get my wave length. That's what I was trying to say. And that lines up quite nicely with this limit that we seem to have in our numerical experiments. I've also done this Pade approximation. And what this means, well, first off, what Pade approximation am I using? Well, there's those exponential terms looking at the propagation of waves across my flow. And this is what I'm using the Pade approximation for. And the one I'm using is just the first two linear terms on the numerator and the denominator. And what this is showing, I guess, is that this red limit is kind of agreeing well with the limit of the Pade approximation as the L gets small as well. So we should be able to approximate this in some way quite nicely. And hopefully it gives us hope that we could obtain this limit by some kind of Taylor expansion or not. In the attenuation rate, we get good agreement as well with our homogenized limit. We also get good agreement with the large consolidated limit as well, which I guess is just a curious fact about the well, if my attenuation rate, if looking at the propagation of waves across the flow and my flows are really long, then that attenuation term dominates and we get back to my original alpha con essentially. You might also notice that we do get some kind of weird resonances because of a periodic media, but that's not important for trying to recapture this kind of numerical experiment. But it is curious and interesting. Okay. Does that make sense? Is that good? Yeah. Okay. Sometimes I go really fast. Okay. The only difficult thing about that P that I showed for the transfer across the flow is that the dependence of P on L is unclear. And what I mean by this is that my L term affects the reflection and transmission coefficient. So it's hard to pull apart and kind of do some suitable expansion to get the limit. Instead, what we want to look at is a different formulation of the transfer matrix by considering the transfer across the edges of your flows, well, of the cells, essentially. So we have some wave in blue, and we get some transmission across the edge TE, and some reflection from the edge RE. And so this is like the transfer matrix from the left-hand side to the right-hand side of this flow edge. If we suitably reflect this problem, then we can form the transfer matrix across the whole cell, which is what I've written here. So we have some reflection matrices reflecting the problem a little bit to give us the reflection across this right-hand side. We have now, and importantly, I guess, is that this PE doesn't depend on my L now. It doesn't know about the flow lengths. And so I can look at this, and all the flow lengths terms come in my propagation across the cell, which is given by these terms here in the diagonal matrix, which I can talk on nicely. Oh, I actually made a mistake, didn't I? Because this should be like a negative.
Those are identity matrices.
What?
First line.
Yeah.
expression.
Yeah, these are eyes and not ones, I guess. Yes. That's an
We
important.
need to know the reflection coefficient in both directions.
Yeah, so it's a symmetric problem, which is why we can kind of do this suitable reflection of the problem using these reflection matrices.
But basically, it's a problem with transfer lines. The transfer line is one is
Exactly. Yeah, exactly. Yeah,
I mean, the whole problem is symmetric, right? With the cell, and then the stuff out here. If I just look at a single interface, the things that you're doing.
Yep.
Then why should the reflection coefficient, that you draw it, be the same if I send the instant wave in this way?
because in my media is uniform. So you do get the same reflection transmission. Now, in general, you don't, and the numerical method could handle this, but it's a bit technical. But if you kind of just like, this is a wave in an ice cover, this is a wave in the same ice cover, and it's likewise on these two edges. So it actually turns out to be the same reflection and transmission coefficient.
Oh, yeah, it's the same material.
Yeah. Okay, and then we could do our trick and find Q based on the eigenvalues of P. And importantly, I can Taylor expand this term, and after dividing through by L, when I find Q, I just have to look at my linear term, and that should give me my limit as L goes to 0. And that's what I've done. So in red, we had what I showed before, good agreement with numerical results. And now in the dashed green line is that kind of linear Taylor term, which gives us the limit as L goes to 0. And it agrees quite nicely. So that's good. Just based on a single cell. Okay. Oh, maybe. Does anyone have any questions on it? So what about the amplitude? Well, this one's actually the easiest, so maybe I should have said that at the same time. But if we just think about the transfer or transmission of waves from my free surface to this new homogenized media with some wavelength Q, I mean wave number Q, which is complex. And we can consider this, just apply the continuity of the velocity potential and its first derivative. And this gives a very simple relationship for what the transferred amplitude into my homogenized regime should be. So it's just dependent on the wavelength in the left-hand media, which is my free surface waves, lambda W, and this new homogenized wavelength as well. Although I haven't taken the real part because the math says not to, so, but it's very small compared to the real part. And there I get good agreement as well. So in red was the Q found via the P for the whole cell, which I showed before, and then the Pate approximation, which gives us some hope that that limit exists. And then in the bottom, I've got the red from before, and that new just looking at the first Taylor term, which gives me my limit as L goes to 0, and it agrees again quite nicely with the results. So happy about that. We kind of looked at all three things of interest, and so we're very happy about that. Oh, I didn't. Yeah, so Experiments show wave and ice predictions during ice breakup events must consider the attenuation rate over distance, but also the amplitude drop as you go from different media in your ocean, essentially. My mathematical model replicates the increase in attenuation as my consolidated ice breaks up, which we saw in the experiments, and the decrease in amplitude drop as well, i.e. more full transmission into a broken ice cover, which we'd expect. Consolidated limit is predicted by a modified classical model, and then we can actually obtain the fully broken limit just via a transfer matrix across a single cell. Very happily done. And what I was just stopped myself from doing is I have produced also how this changes. Since I only sent in one frequency wave, I've looked at how the different frequencies change. But I didn't actually make those pictures, but I could plot them now if anyone's interested. But otherwise, feel free to ask questions. And dangerous, isn't it? Yeah, that's what.
There are questions for Jordan.
About this, about this observation, I noticed that the examples that you have shown, the affiliation in the case of this rate of MWS as compared to solid ice, is 3 times greater than the other one. Is this 3 times somehow significant, or if you change the parameters of your problem, is number?
Yeah, so I guess this is kind of one direction is looking at how it changes the frequency. And when we see that the longer your period, your wave is, then the less effect this has. And they all kind of approach one another.
Can you go back?
Yes, it's not consistently 3, but that is a significant difference.
Yeah, well, for example, so we have this alpha equals 1 multiplied by 10 to the power 3, or 3 multiplied by 10 to the power 3. So in 2 cases they differ by 3 times.
Yeah.
Is this doesn't have a significance?
No, yeah,
It's
no,
a magic number.
yeah,
So it will change if you change the.
yeah, absolutely. Yeah.
Not right. Nice to know.
Oh, yeah.
This might be too low.
Yeah. The start out below 1. It's pretty close.
Yeah, but it's not consistent. Like, yeah, you change some parameters, you're going to get a different relation. And indeed, it's not going to be linear at all. That is the case, yes. So this kind of qualitative relationship is. Yeah, so we've kind of applied a very simple dissipation mechanism, the Robinson-Palmer damping, which just gives you a fixed rate of like friction as the plate bends, as waves propagate through it, which.
When you block your ice, it's small pieces, they don't bend anymore.
No, they don't bend.
What happens? Why do losses higher?
Yeah, so the loss is higher, we think, mainly because the wavelengths are smaller. So we have some kind of constant damping rate, and then my wavelengths
So
have decreased.
You want to say that your wavelength is the same damping still? No.
Well, there isn't an effect you get purely from multiple scattering. Stanislav. If you purely multiple scattering,
Sure.
you can do this piecewise approximation. So when the wavelength is large, you don't see local variations. But as you get closer, you get effective attenuation. If there's some attenuation in your motion, you would expect that from multiple scattering. Although
It's not related to dissipation and the stochastic forces.
it's more of the fact that it's broken, so you can have short contrast between neighboring sites.
Broken sort of consolidates, but the distance mechanism is the same. But the wavelength is changing. So I also imagine you moving your complex wave number around and complex wave number space, right?
But for me, I'm just trying to understand the physical. What's wrong is my confidence. The physical mechanism of this exploration. So if you say that the definition comes mostly from the ice itself, right?
Mhm.
That's the problem. And then you say that there is certain force associated with the elastic deformation of this ice. Now, if I imagine that I have broken this ice and made many small pieces, each piece I think now just moves by itself without the elastic deformation.
But
And
that's
then
that's earlier, I think.
Then this loss mechanism somehow is a hindrance, right? At least I may be completely wrong.
Yeah, so I mean, if you think about it physically, right? So I've taken the gaps between very small. So the ice, we haven't actually lost any ice. I'll go to the dispersion relationship. So actually, that kind of mechanism of attenuation rate over distance is still there in each flow. Now they're very small, but the point being that my wavelength gets smaller. So I'm seeing more of an effect of the same gamma, essentially.
Yeah.
Hmm.
On the imaginary units and points of it, that's a down thing, right? So that's not connected to the bending. It's just the up down one.
Hmm.
It's even it's a feature of the law.
What feature of the model?
But that, I mean, that's your chosen.
Yes, exactly.
For the fine.
Yeah, I mean, maybe there is some argument that it's not a good model, but but it's what people use. I mean, and they're doing even more dodgy things than this. Oh yeah, maybe I shouldn't say that.
I'm gonna be more positive. That's right. You can put down
Yeah.
into events, people have done that. It does not compare well to measurements. It changes far too steeply with respect to previous. This is what myself as far as show. This damping term is almost certainly incorrect, but it's probably closer to being correct in that it gives you the right sort of previous independence. You can't put the damping with a higher term and not get that really steep response with respect to previous. We throw it in because it's the best thing available at the moment, and just to as an illustration of the sort of best that you get.
So this damping is just the damping proportional to the losses, right?
Yeah.
This Z is the velocity potential with respect to Z. So this damping depends on the vertical velocity, right?
Yeah, in the story behind it, but Robinson Palmer, I think both of them came from their engineers, and they were doing something like vibrations or pink cat or something like that, where they were looking at the vibrations of the leaves. And they came up with something like this. And 20 or so years ago, something CI still was looking around the sorts of dampings they put in there, and I'll put that in. And no one's got a better one, amazingly, as compared to illustration data. But you can see stuff like that. There's nothing about the ice in there. There's this gamma in there, right? That you just choose to experiments, but it should depend on things like ice thickness. But nobody's derived that yet. Okay, there's a lot of debates in the field about these things. So we're kind of distancing ourselves from those debates and looking at other people just chucking the best things that we can have.
This expression, I think what could happen, what is the difference here in the situation when the ice is solid, the ice is broken, and this is how it is having this direct from its middle.
Yeah, well, this is what you were saying before. Well, like in the sense that your gamma is not changing, but the wavelength is changing in your media. Yeah.
It's in the marginal stage.
Yeah, it's in the connection. Sorry, actually, it's.
Can you explain? How do you see
So if you have this equation is a small pieces of broken parts, and every Monday, let's say, these pieces of ice, you have to luminescent terms, right?
Well, yeah.
So those luminescent terms, they will go of the higher values of the velocity, local velocity at those points.
Yeah,
And then he remains in construction.
look, that's a good thought. I'll tell you that the results I used reject or omitted all those evanescent terms. So actually, so it's in the numerical results. Sorry, I should say it's in those. It's in my yellow dots, but it wasn't in the. It's not in my red curve. There's no evanescent waves in the red, but there are in the yellow. So actually, it doesn't make any difference.
Very general.
Yes. There's not much reflection and transmission to those modes either. Yeah.
Give the observation point out,
Mhm.
and so if I'm thinking that,
Sure.
say, effectively you can base it on Einstein, the boundary condition, given somewhere at the bottom, down certain functional equations in the top. I don't know, maybe it's been done. I mean, the boundary condition that he has on the ice is a dependent boundary. Exactly, but in the calculations, we define my thickness and like that. Yeah. But I don't think there's anything about the thickness of the ice.
Not in the bending.
Well, not geometrically, that's not confused, right? So I mean, thickness goes into the dispersion, right?
Yeah.
Right. The geometry very weakly goes. It's a very strange thing, actually. So not using is applied on the zero.
Yeah.
Well,
Well, actually,
we don't.
it's a bit. No, it's actually a D, I guess, negative D.
That's what I'm saying.
Yeah.
And what I'm suggesting is to take D, yeah, it might vary the difference in terms of numerics. That's what historical reason. You get a mixed boundary value, like in an arm space, because of depth of the water in the depth. And then that's what you're getting. And if you get broken ice and you have this simplified configuration, and you have propagation in one direction, it's not a picture and then three-dimensional map of broken pieces of ice, but specified system of broken ice, so you have stratus of the ice. And if I think of this as plates connected by the pins, say, yellow one, no resistance, but of course each plate is going to require the plate. And again, you can set it up nicely with the video structure and problem that. But you can, for infinite depth, it will be effective in the concentration. And if the depth is fine, right? But the layer finds to thing. But of course, we will get more complicated panel. So I'm just struggling to think of what we're doing hot for you for the what we're presenting here. Oh, you have change your boundary condition. You have change your boundary condition, and you have semi-defined and from the surface you change to the boundary condition related to the threat. And well, let's take the transform the transform set up. And you can create your equation in terms of one side of the transform, and you will solve the problem in the same. Well, I'd be very interested. I think for me at this point, I need to go to a board with you and start writing this stuff down. And I'd like to understand more. Actually, see if anyone else has a question.
The other question is, like, the difference, suppose the depth is small. The observed effects line for the hand. Then you have blockage.
Well, I must admit, I haven't looked at it. My depths are really large compared to my thickness of eyes. I haven't played around, and certainly it's not as interesting from like an applications point of view, but I'm not sure. And like, you mean like an impulse of like a series of random waves and then nothing, or you mean like an impulse? Right.
Agree that's that. I would agree that that's the monument properties. Experiments.
Yeah. What period?
There's no way.
Yeah. Yeah.
What does it? Experiments. They contain some information. You know. Once we did that,
What would the impulse give you over just sending in random waves, essentially? Does it give you more information or something?
There's an initial kind of impact.
Right, I see.
Because
Mhm. Right, yeah.
that is different from
Okay, yeah. We have some experimentalists that, oh, not experiment, I guess observationalists that'd be very keen to get something like that.
because it's neither takes out the ice.
Yeah.
It's so it's not.
Mhm.
Another question?
Yes.
Yeah, it's the same comment, but they here. Less than classified.
Oh, yeah.
What is also, as part of is that there is some kind of angle of incidence.
Yeah,
Say, which is not these, there needs to be experiments we had to just a normal incidence.
Mhm.
Anyone who could,
Yes.
we have.
But, I mean-
Track.
I mean, in terms of waves into an ice cover at oblique angles, yes. In terms of the results I showed, no. But it's,
Quite a nice picture of the video.
yeah.
Yeah.
Well, that's like-
There's a whole YouTube video that's quite nice.
Yeah, yes. Probably on the same wavelength as the lots of.
They're definitely related. The wavelength and the sizes you get in the brain.
The vessel is much longer than.
Yeah,
And I think you could also consider the case when the wave is incident comes inside of the device. not on the side of the water.
Right.
It's a interesting problem. So you can just take the base.
Yeah, there's always clearly a selection in regard to the size of the organisms. You know. They're
Hmm.
not totally even.
Yeah.
Oh. Look at these things, isn't it? Really, so, yeah, or something, I don't know.
I mean, they consider, like, been to some of their talks, and they consider lots of different things.
There's some selection.
The past history of the way the ice formed and any cracks pre-exist or weaknesses in it. That's something else they think about. There's a lot of different things going on in the ice cover. And it's all somewhat related, but it's just out of reach.
Yeah, to be more specific, what I mean is little bit something to fit. Sounds beyond what we hear.
It's residue calculus stuff. Some work as well. That's part of it. Just as one grapple.
Yeah, that I'm not saying that it will have this split, but what I mentioned. That's
Cool.
Yeah, let's chat about I haven't had that 20 years ago. All right, there are no further questions. Going. John, right, thank you everyone. Let's thank you again. We'll be back here next week in our regular time for seminar.
Excellent.